Hey guys, this video is going to introduce us to some of the math that has to do with dropped objects. Um, so what is a dropped object? It starts at rest in our hands. You don't throw it up or downwards, you just let it go. So the initial velocity of a dropped object is always going to be equal to 0 because you just let it go, you don't throw it. Okay? Whenever you let go, the object accelerates. Like if I have the pencil, its initial velocity is 0, but the speed is going to change. It's going to increase once I let go. So they do accelerate, meaning they change speed once you let go. Why do they accelerate? Due to gravity. Gravity is what speeds it up. Or if we do tossed up later, that gravity will actually slow it down as it rises. But today for dropped objects, it's a speed up kind of acceleration due to gravity. Now, depending on what planet you're on, the acceleration due to gravity might be more rapid. And the rule is, well, let's look at the numbers here. On Earth, the acceleration due to gravity is 9.8. On the moon, it's just 1.6, so less on the moon. But on Jupiter, it's more than Earth. More acceleration, more rapid acceleration. 24.8. And on Mars, not as quite as small as the moon, but definitely smaller than Earth's acceleration. Alright, so what does this mean? Well, which one of these is the largest body or planet? Yeah, Jupiter is the largest. So a larger body or planet is going to have a higher acceleration due to gravity, which means it gains speed quicker on Jupiter when you let it go. But which acceleration due to gravity is the smallest? Well, it's on the moon, and the reason is that the moon is it's not a planet, but it's our smallest body out of these four, okay? So the moon is the smallest because it is the least massive planet or body, all right? So when you drop something, it will speed up, but not quite rapidly on the moon. It'll slowly gain speed on the moon. So the unit of all these numbers, since they are accelerations, is meters per second squared. Okay, and what do those numbers mean? Well, let's take Earth as an example, and let's use that number to be like about 10. So if we think about that as the number 10 instead of 9.8, because it's pretty close to 10, what that means is that after you drop something, after it falls for 1 second, how fast is it going? What does the speedometer say on my pencil after 1 second of falling through the air? The speedometer says 10 meters per second. But after 2 seconds, what is the speedometer? If I had a speedometer attached to my pencil like you have in your car, what is the speedometer going to say after 2 seconds? Well, it's going to add another 10 onto it because that's what the acceleration says. So after 2 seconds, it'll be going 20 meters per second. And after 3 seconds, the speed will be 30 meters per second. And after 4 seconds, you keep adding 10 more meters per second. So after 4 seconds, it would be going 40 meters per second. Now compare that to the moon, though. Where on the moon, you only add every second how much speed gets added. Just 2 meters per second of speed. Because that number, 1.6, is about 2. So after 1 second of falling, my pencil on the moon would only be going 2 meters per second. And after 2 seconds of falling, it would be going, that's right, 4 meters per second. After 3 seconds of falling, it would be going 6 meters per second. Still not that fast. So it's not a rapid acceleration because the moon is a smaller than all these planets. Now Jupiter, that's about 25. So after 2 seconds, it would be already going 50 meters per second. It would say, that's quite fast. Even after 2 seconds of falling, something on Jupiter would be going 50 meters per second. All right, so you kind of see how that works. Jupiter is very rapid. The moon gets adds 2 meters per second of speed only every second. So it's kind of gradual increase in speed on the moon, really rapid increase in speed on Jupiter. So these numbers are with no air resistance. It's important to keep in mind. Air resistance would make those numbers a little smaller. So equations. We're about to use these equations in our next video. So these are modified from the kinematics equation. From the first kinematics equation, since VI is 0, we could take that out. And acceleration we're going to replace with g. So acceleration due to gravity, we should say that's also called g, all right? So depending on what planet you're in, if you're on Earth, you plug in 9.8 for g. For the moon, you plug in 1.6. For Jupiter, if I say in the problem you're on Jupiter, you plug in 24.8. T is the time an object falls for. D is how far it falls during that time. So that'll get you some relationship between distance and time, where you could plug in these numbers for g. And then there's an equation to get final velocity equals just g times t. So those are the two equations we're going to use. We're going to simplify it. For dropped objects, just use those two equations to relate time to distance or time to final velocity. And gravity, which is these numbers, can be plugged in here. Usually we're going to use 9.8 because most of our problems will take place on Earth.